now, black body radiation. You have to imagine a black body as a body that is black. When it is black, I think the ones that studied physics before, they know that black absorbs the most energy, radiation energy. So it's just a theoretical idea saying that a body that is black, that will also absorb all of the energy if any energy comes upon it. Any radiation that comes into the black body will absorb all of it. But that's a theory or a concept only. But we use this concept to describe the surface or the state of that object. So a black body is a surface that completely absorbs all incident radiation. Maybe there is an object that does absorb all, but that is, I think, an ideal case. Okay, but some objects can be considered as a black body. Maybe things that are in space that is able to absorb all incident radiation or any radiation that comes into it. Now, a unit of a black body value, or a certain parameter that we use to describe the black body surface, is this unit megawatts per micrometer per steradian. So when it says per micrometer, it's for a certain wavelength or a certain color. Per steradian is for every solid angle, for a unit solid angle. Now we look at this graph. This black body would also, it absorbs, but then it also emits radiation. We can think of it as being as something that a surface that emits the radiation, because here we see the black body value with the unit megawatt per meter square per steradian and so on, and the wavelength. This graph shows that, can you see more or less? So this is B lambda, the black body value for a particular wavelength. And then this is lambda micrometer over the wavelength. This is the intensity of the black body, and this is just a different wavelength. And the different wavelength is for different colors. You notice that for a wavelength less than 0.5, the black body radiation value is small. But then as you go up higher, then in wavelength, then the black body radiation goes up to a peak value and then start to decrease. And then we see the same trend for these different curves. Now the key features here are this peak here in the middle. And another thing is that if the black body has a certain temperature value, the amount of radiation that escapes it, the black body, or we don't want to say escape because it absorbs, right? But just the amount of temperature that is on the black body would be high at a certain wavelength. So if the black body is at 5,000 Kelvin, then the black body value is about 11 or so. But as it has higher black body value, it corresponds to a higher temperature range. So if the black body is at 7,000 Kelvin, 7,000 Kelvin is very hot, right? 7,000 minus 270 is about 3,700 degrees Celsius, 6,700 degrees Celsius. The black body value is higher. Actually, from here, we can denote a temperature of a surface just by knowing the wavelength, right? This is what it means in terms of application. It means that if we know the wavelength and we know the black body value, we can guess the temperature. And that's how scientists have found out the temperature of the sun, just by knowing the wavelength and the amount of intensity that reaches the Earth. Right? We don't go there and measure, right? You get information from radiation that comes to us, and that's how they study space. So this is one of the ways of how they measure a temperature of a surface or a temperature of anything. It doesn't have to be the sun. It can be, no, it's just a pencil box. Don't worry. You'll survive the fall, I think. And that's how they guess the temperatures of different planets, of different objects in space too. That's quite interesting application there, because they relate radiation to temperature. Now, how do we calculate this curve if we want to know how it behaves with micrometer? You notice that it's follow more or less standard curves, right? So we can describe this using an equation, and that is the equation. The black body for a certain color, which is a function of temperature. It looks complicated, but most of it is made up of constants. You just plug in the value. It's just a constant value. So this black body value equals to C1, which is this value here, a constant, times the wavelength, divide by pi, which is another constant, exponent C2, another constant, lambda is the wavelength, temperature. This is the key thing. If you change the temperature here, the peaks change to n minus 1. And if you have, let's say, 7,000 K, you plug into this equation, and this lambda here, you change from 0 to 2, and you calculate this, you should be able to replicate the curve. Now, this question is interesting, or this example is interesting. It comes from this Wallace book. It's directly lifted off of this book. So the solution is also there. So this example asks us to use the Wien's displacement law to calculate the color temperature, in inverted commas, of the sun. That means you want to find or guess the temperature of the sun, for which the wavelength of maximum solar emission. Remember this curve? Oh yeah, I don't have to draw this because you can see it there. Notice the curve is at its maximum at a certain wavelength, right? That maximum wavelength is observed to be approximately 0.475 micrometer, which is again in the visible light wavelength range. Again, the visible light wavelength range is between 0.4 until 0.7. So this is somewhere in between. And when we look at this graph here, we see that this peak is usually somewhere slightly lower than 0.5, which is about this wavelength range, right? So we just use that simple equation that comes from Planck's function, derivative of the Planck function, which is the, let's see, before that, what was the equation again? Oh, okay. The original equation is the maximum wavelength is equals to a constant 2987 divided by, okay, thank you, 2897 divided by temperature in Kelvin. So we have this maximum. So we want to calculate temperature. So the temperature at maximum wavelength is simply 2897 divided by 0.475 micrometer. There is a unit here that cancels micrometer to change to Kelvin. I think the unit should be K micrometer, where you can cancel these two. So that is the unit of this 2897, although it didn't state it there. Okay, so what is the value here? Once you finish calculating? 6, what's that? 6 what? Huh? 6? Whatever. Okay. So just for your information, if this is at 3 decimal points or 3 significant figures, then our answer should be in 3 significant figures. So this is at 4 significant figure. So this one rounds up to Kelvin, because we use this 3 significant figure value. So that is the color temperature of the sun. So this is another example from the book, an excuse for us to use the Stephan-Boltzmann law. Here the question states that we need to calculate the equivalent black body temperature, TE, of the solar photosphere. That means the outermost region of the sun that we can see, the visible part of the outermost region of the sun or surface of the sun, or the photosphere. Based on the following information, the flux density, or F, of solar radiation that reaches Earth is 1368 watt per meter square. Notice the unit, watt per meter square. The distance d between the Sun and the Earth is 1.5 times 10 to the power of 11 meters. And the radius of the photosphere of the Sun is Rs equals to 7 times 10 to the power of 8 meters. So, calculate TE, the black body temperature, or the black body equivalent temperature of the solar photosphere from this information. Now, the hint is we need to use the Stefan-Boltzmann law, F equals to sigma T to the power of 4. How do we do that? Yeah, the equation is there and the constant is there. Okay? Anybody has any idea on how to do this? If you have the book, then you will have an idea because of the answers laid out. So here, using this equation, we want to calculate T, the black body equivalent temperature. So we have F, and definitely we have sigma. But then there's a few other information here, right, that we need to use as well. So we need to modify, the strategy is we need to modify F here so that we get the actual F, and then using the F, we divide by sigma to calculate T. Right now, the F that we have here is the F on Earth. 1368 watt per meter square is the F that we receive on Earth. But we want to calculate the F, we want to know the F at the Sun, because we want to calculate the black body temperature of the Sun. Okay, why we use the Earth? Because obviously we don't measure F at the Sun. We measure F here and we guess F at the Sun using an equation, using a ratio. So the strategy is first calculate the actual F. Once we calculate the actual F, then we back calculate T. Does that make sense? So can I rub this off? Can, right? So I have enough space to do the calculations here. You want to calculate F at the photosphere. We don't know that. We just have F on Earth. So F photosphere is equals to F on Earth. I think just now we use Fs. But not exactly. This is definitely more than this one, right? So we know the relation between the F at the Sun and the F on Earth is just based on a ratio of how far the Sun is from the Earth. So that ratio is just the radius of the solar photosphere divided by the distance from the Sun. So let's say this is Earth and this is the radius of the photosphere. Up to this point, Rs, and then the distance. So this radius divided by the distance gives us the ratio that relates Fs to this. Okay, but then there is this relationship, because remember that one slide. Remember this slide? Oh, wait. The angle covered by the Sun is inversely proportional to d to the power of 2. That's where we get this from. We multiply with diff SS, then you get the F photosphere. So this is 1368. What is RS? 1.5 times 10 to the power of 11 meters divided by D, which is 7.00 times 10 to the power of 8 meters, power of -2. I think there's a typo here. RS is... Oh, no, this is the same. It's just that it's inverse. Yeah. Well, if you want it to be -2, then it will just be the other way around. And you should get 6.8728 times 10 to the power of 7 watt per meter square. And that is the photosphere, the F of the photosphere, which is a lot higher than just 1368 on the surface of the sun. So now we have the F photosphere, that we can calculate the black body temperature using the equation F sigma T to the power of 4. Sigma is that constant value. Yeah, 5.67 times 10 to the power of -8. And then the temperature is what you want to calculate. And this F here is 6.28 times 10 to the power of 7. And we get T after you you root it by 4, and you get the temperature. So the temperature is? It's about 5770 Kelvin. Now this is another temperature for the sun. Compare this with the temperature we calculated before using Wayne's displacement law. What was that? That was 6,100. This is 5,770, about the same value, plus minus 300 degrees, 300 Kelvin. But it is slightly different because the spectrum of the sun's emission differs slightly from the black body spectrum. So this is the black body spectrum, but the spectrum of the sun is slightly different. So that's why there is slight variation. The one that we calculate using the Wayne's displacement law is the actual spectrum. Well, this one is the black body estimation. And that's why it's slightly different. But again, it's quite close to each other. So we know it's about 6,000 Kelvin or so.